Hi people, this is video 3 for derivatives and logarithms. First video was on the derivative of logarithmic functions. Last video and this video, the concentration will be on logarithmic differentiation, which is the introduction of logarithms into a function that did not previously have them, so that you can use them to change the form. And so let's go ahead and jump right in with a couple more of examples. This one is kind of like examples in the past where I like to put two different functions together that are composites of the same two contributing functions, one being f of g of x and the other being g of f of x. So this one right here, let's go ahead and take the log of both sides. And that winds up giving us a product rule over here. So y prime over y. So we have the first times the derivative of the second plus the derivative of the first times the second. And I have y prime is equal to x to the cosine x. And you can simplify this first one however you want. I would choose to go ahead and put it as cosine x over x minus sine x natural log x. And that right there is your derivative. Now let's see how it looks when it's the other way, okay? And I take the natural log of y, and I'm going to get x times the natural log of cosine x. Still a product rule, but, you know, this one winds up being a little more complicated. So we have y prime over y when we differentiate both sides. We'll have the first times the derivative of the second. So we'll go ahead and plop that argument down here in the denominator, putting its derivative in the numerator. And then the derivative of the first times the second. And to round it all out, we will go ahead and multiply both sides by y, which of course is cosine x, all raised to the x power. And this one, I'm going to go ahead and reverse it since this is negative right here. I'm just going to change the order. Natural log cosine x minus x tangent x, and that just makes it look a little bit prettier. But if it were negative x tangent x plus natural log cosine x, same thing, right? Sometimes I change the form just because I want to look at it in a particular way. So don't worry about that too much. Let's do two more before we go on to our tangent line problems. We're going to be doing one problem that it's probably advantageous to use logarithmic, and then the other one is going to be necessary. So if we introduce natural log here, of course, this whole thing, right, is to the 1/2 instead of the radical. So we have 1/2, and let's just put a big bracket down here. Now, remember, every single factor of the numerator gives us a positive logarithm. So natural log x plus natural log x plus 2. And every single factor of the denominator gives me a negative logarithm. 2x plus 1 minus natural log 3x plus 2. Now, this was going to be really nasty in its original form to differentiate. This, however, winds up being relatively straightforward. The 1/2 kind of comes along for the ride, and I get 1 over x plus 2, 2 over 2x plus 1, and 3 over 3x plus 2. Right? Because each one of these, you take the argument, throw it in the denominator, and if necessary, put its derivative over it. And I guess you do have the derivative of x up here. We just don't usually talk about it that way because it's nothing more than just x, right? And you do have the derivative of x plus 2 up here in the numerator. But you do need, very specifically, the derivative of 2x plus 1 up here, which is 2, and the derivative of 3x plus 2, which is 3, up here. Now, y prime just winds up being 1/2, and I can go ahead and put it back into its radical form because I'm not going to do anything else with it. And if it was originally in that radical form, then maybe it's a good idea to leave it that way. and I have 1 over x plus 1 over x plus 2 minus 2 over 2x plus 1 minus 3 over 3x plus 2, and that monstrosity right there is indeed our derivative. I have this I kind of want to do it the long way just to show you. Actually, I tell you what, let's go ahead and do it the long way. It's obnoxious, and I'm going to basically show you this. So, as a way of encouraging you to, study your logarithmic differentiation and to know it well. And 3x plus 2 all raised to the 1/2. Okay, let's do this the nasty way. Y prime, and this is stuff to the 1/2, so it's 1/2 stuff to the negative 1/2, okay? Now I need to go ahead and do this by the quotient rule, which is obnoxious. But I guess it would be a little bit easier if you were just basically turn this into x squared plus 2x and turn this into x squared, 6x squared plus 7x plus 2 to the 1/2. That might make things a little bit easier. And you wind up with, start with the denominator. Times the derivative of the numerator minus the numerator times the derivative of the denominator. All of that over, 6x squared plus 7x plus 2 squared. Okay. Now, then you have to basically clean up that numerator to see whether, terms combine, terms cancel, and stuff like that. I would actually go ahead and I would flip this over. I mean, I would keep the square root. So actually, you can call it the square root of that, because the 1/2ness of that exponent is the square root. The negativeness of the exponent is the flip me over. So if you flip it over, then you can redraw it as a radical. I'm going to have to basically multiply this binomial by this trinomial, which of course nobody enjoys doing. Well, I mean, some people probably do. Plus 12x squared plus 14x plus 4, and see, I'm already running out of room. And then of course you have to deal with that negative, which then of course needs to be distributed across whatever this product is, 12x cubed. So that's first outer and inner. So the outer is going to be 7x squared. This is going to be 24x squared, so that's 31x squared plus 14x. Okay, all of that over 6x squared plus 7x plus 2 squared. So yeah, see, this is basically why sometimes logarithmic differentiation, while not necessary, is wonderfully advantageous. Let's go ahead and distribute that negative, and so this cancels out with that. Negative 14x cancels with negative 14x. I get 14x squared, 12x squared, which is 26x squared, minus 31. That's going to be negative 5x squared. Okay. Then, of course, I'm going to go to my linears. The only one that's left is that 4x. And then, of course, the only constant I have is plus 4. And I have 6x squared plus 7x plus 2 squared. And then, of course, you need to venture a guess as to whether that's factorable and all sorts of fun stuff like that. But even up to this point, it's messy. Who would ever want to deal with all of this simplification garbage when this is so nice? So nice. So yeah, let's remember to work on our logarithmic diff, because, it's helpful and stuff. Now, let's go ahead and look at this problem down here. Let's go ahead and rewrite this as y because it's a little more difficult to deal with it as natural log of f of x. Not that that's illegitimate, so that's supposed to... Okay, let's try that again. E to the x, and therefore we have natural log y is equal to e to the x times natural log x. Now we can differentiate y prime over y. First times the derivative of the second plus the derivative of the first times the second. And my y prime is going to be equal to x, e to the x, times, I'm going to go and factor in e to the x out of this derivative, and then I'm left with 1 over x plus natural log x. And while it's not very pretty, at least that's presentable. Okay, now that we've done a couple of problems like this, let's go ahead and take this knowledge and let's apply it to a tangent line problem. This is obviously, we don't have to do it by tangent line, but obviously it's going to be beneficial to do so. So let's do the natural log of y is equal to the natural log of x, right? Because that's the first factor. The second factor is going to give us 2 natural log of x to the 1/3 plus 1 minus 1/2 natural log of x plus 1. Now, let's go ahead and differentiate. So we have y prime over y is equal to 1 over x plus 2 times x to the 1/3 plus 1, and then 1/3 x to the negative 2/3 as its derivative, minus 1/2 1 over x plus 1. So we get y prime is equal to, well, let's go ahead and let's write it again over here. And then we're going to have to multiply it by 1 over x. This one is going to simplify into 2. Now both the 3 and this x to the negative 2/3 are begging to go down into the denominator. The 3 just as a 3, the x as a x to the 2/3, and I still have x to the 1/3 plus 1 down there. And then I can go ahead and put this 2 together with the x plus 1 in the denominator. Now, not pretty, but if I evaluate y prime at 8, I already know what plugging it into this is going to be, right? Because that's how you got 24. Because you plug 8 into here, it's going to be 2. 2 plus 1 is 3. 3 squared is 9. 9 times 8 is 72. But then, of course, you're going to plug 8 into here. 8 plus 1 is 9 divided by 3. So it's 72 over 3, which is 24, which is, you know, what we expected it to be. If the original expression is part of the derivative and you already have the ordered pair, you actually don't have to do that part of the evaluation. I was just sort of confirming that for you. So we have 1/8, and then we have 2 times 3. Now 8 to the 2/3 is the cube root of 8 squared, so that's 4. And then this is the cube root of 8 plus 1, which is 3. And then you have 1 over 2, and then x plus 1 is, of course, 8 plus 1, or 9. Now, all of this is going to be, let's see, that's 1/8. Let's simplify this. This winds up being, this cancels with one of these in the numerator, and so that's going to be 1 over 18. Minus 1 over 18. Oh, that's really, really nice. And 24 times 1/8. 1/8 of 24 is 3. There is your slope. Here is your point. Y minus 24 is equal to 3x minus 8. There is your tangent line. Now, if you were to do this derivative the long way, by the quotient rule and everything like that, I highly doubt the evaluation first of all, the taking of the derivative is going to be more cumbersome. Second of all, the actual evaluation of the derivative at a particular value is going to be not fun either. So this, especially since it's an input-based question that you're asking the derivative, Mr. Derivative, I'm going to give you 8 as an input, give me the output. Now, obviously, there's going to be a disadvantage if you have a derivative strung along into several different terms, asking it an output-based question, but we'll deal with that when the time comes. Now, y is equal to x to the cosine x. In the last one, it was one of those ones where we didn't have to use. In this one, it's going to be one of the ones that we do have to use. So this becomes natural log of y, cosine x times natural log of x. And I've done this one before in a previous page. It might have even been in this video, but let's go ahead and do it again. Can't hurt, especially since, just we're doing it for the sake of the tangent line. We're going to have the first times the derivative of the second plus the derivative of the first times the second. And y prime is going to be x to the cosine x. That's going to be cosine x over x minus sine x natural log x. And if I'm evaluating this at pi, this is going to be pi to the cosine pi. This is going to be cosine pi over pi minus sine pi natural log pi. Well, if there's one thing I know about sine pi, it's 0. So that goes bye-bye. Pi to the cosine pi, well, cosine pi is -1. And cosine pi, again, here is -1. So what I have here is 1 over pi times -1 over pi, or -1 over pi squared. Now, probably not your favorite number, but it's not notationally gross to look at. So we have y minus 1 over pi is equal to -1 over pi squared x minus pi. And as obnoxious as that looks, that is the equation of the tangent line to this curve at this point. Okay. Alrighty, guys. Well, that brings us to an end for the videos on derivatives and logarithms, both derivatives of logarithmic functions and logarithmic differentiation. Please do let me know if you have any questions. Shoot me an email. Bye.